Okay.
Yeah. Thanks for having me here. So yeah, so let me give you a different flavor of these geometry, particles, and so on. Namely the enumerative geometry and some invariants. So I will talk about the stable pair invariants and their connections to Downs and Thomas invariants over K3-fibrations. So this just to start with the geometric setup. Let X is smooth, projected threefold on C. Now for betas, integral homology, some second integral homology of X, and some integers, and we define the moduli space. The moduli space, I call it, this moduli space of the stable pairs, introduced by Thomas, or and Thomas is famous for PT moduli space, these things. So these things denoted by, so these depend on these numerical data, denoted by Tm x beta. Parameterizes pairs of an S, or namely a sheaf and a section like that, a morphism in the category of coherent sheaves on X, where F is a pure coherent sheaf with one-dimensional support, one-dimensional support on X, support in X, and on X, with homology class equal to beta. So support of F has homology beta, and this integer n is going to be for us the Euler characteristic of this one-dimensional sheaf. Okay, and moreover, by some stability condition, that these are pair stabilities, they call them. We would like this section map to satisfy the condition that, moreover, by some stability condition, co-kernel of S is a zero-dimensional sheaf.
So just this is surjection in a different structure.
Yes, that's right. Exactly.
P means Kern-Macaulay.
Yes.
And is it important that X is a threefold? I mean, they have this model space for
surfaces. Yes, you can add it for surfaces. And okay, so probably these things are really known and almost classical these days. Gauss-Thomas theory, but just to remind you, all of these theories, these are auxiliary theories to, I mean, in my point of view at least, when you look at the literature on it, they are auxiliary theories to understand Gromov-Witten theory. Koncevich's moduli space of the stable maps had some little issue, which was that, so you're looking at moduli space of the smooth curves embedded inside an ambient threefold, and this is open, the moduli space. And Koncevich came up with a compactification of this moduli space by looking at the stable maps. So stable maps, the stability condition, if you really zoom into it, kind of is giving you a way of controlling the singularities of the curve in the limit. Okay, so because of the automorphisms of the curve, the Gromov-Witten invariants, which are intersection numbers over the moduli of the stable mass, are rational numbers. But all of this story came from a Feynman path integration formalism in quantum gravity. And string theorists really wanted to calculate integer values for these invariants. The Gromov-Witten invariants do not have integer value. So the story is that physicists conjecture that maybe there's an underlying set of integers that could capture these Gromov-Witten invariants and could have enumerative meanings. Obviously, rational number doesn't have any enumerative meaning. It doesn't have any meaning to say I embedded 2/3 of a curve inside, right? So, but integer does. So that's what it means, enumerative. And so Johnson-Thomas invariants were a mechanism to get these integer valued numbers. So just instead of looking at curves inside the ambient threefold, you look at ideal sheets of curves. And the ideal sheets are stable objects, and so they don't have automorphisms, and so you will get integer values in 1 by 1. The problem with ideal sheets was that you kind of a little bit lose touch on Gromov-Witten invariants, because ideal sheets, pictorially speaking or topologically speaking, look like not just naked curves, but they could be given by pure one-dimensional subschemes, non-pure one-dimensional subschemes, which could be curves and some reduced structure. So zero-dimensional pieces attached to them. So these zero-dimensional pieces could be on the curve or off the curve, and so that's why the moduli space that Richard Thomas wrote his thesis about is the Hilbert space, a one-dimensional subscheme device. It looks like space-time Chinese. So there was an honest kind of intuitive relation everyone was thinking of between this picture and a picture of just curves like that, maybe with points on them, and that was removing these points off the curve. And so these stable pair invariants are basically algebraic objects that parameterize pictures like this. An example of a stable pair is that if you have a curve and only a divisor on it but not off of it, if you have some curve and some divisor in it, like this, of course this defines a line bundle on the curve, like that. So it naturally gives you a section, and then you can embed everything inside the threefold, so like that, and then you can compose map, like that. And you can see that this is a torsion-free sheaf and a locally free sheaf, in fact, on the curve, but in the ambient threefold it will be a pure sheaf with one-dimensional support. And on the curve, the co-kernel of this thing is just a skyscraper sheaf of this point. So if you now think about this part, you will get the ideal sheaf of the Cohen-Macaulay support of your sheaf, and so that is the stable pair. So you get something like this. You get some complex, or we'll put a sheafed section in the middle. I can call it F, which is in here, some push forward of this line bundle, and then a skyscraper sheaf of pure point. And, not every sheafed section does satisfy this condition, of course, but we would like to actually glue this kind of point of view to Gromov-Witten theory, so we put some stability condition which guarantees that the co-kernel is good. Okay, so this is a stable pair invariance, and my story is about the stable pair invariance of K3-fibrations. Okay, so now let X admit morphism. Pi thanks to C with K3 fibers, where C is smooth and projective. Okay? And the fibers are generically smooth K3s. So nodal K3 fibrations, for example, they need to have generically smooth fibers. but finitely many nodal singularities, but I will discuss that later at the end of my talk. So let's assume that this X is a K3 fibration. It doesn't need to be a Calabi-Yau threefold. Okay, now here we always take beta to be the kernel of pi over star denoted by vertical curve classes. So these are curves. This cohomology class comes from the fiber. So we are interested in K3 fibrations, and we are interested in one-dimensional subschemes algebraically given by a sheaf and a section such that this sheaf is supported on a curve on the fiber. Okay. The virtual dimension of this moduli space for such choice of beta, the vertical curve classes, is 0. Is 0 for such beta, regardless of X being the Calabi-Yau. Often virtual dimension 0 property comes from seriality. The virtual dimension is what is kind of, roughly speaking, the difference of the dimensions of deformations and obstruction to those deformations of the points of the modulus. Okay, so these objects are, there are complexes, there are objects in the drive category that represents a sheaf and a section, and the obstruction theory of this thing is captured by some R-Hom in the drive category of the moduli space, which is the self-extensions of this object in the drive category. We are not saying that we are parameterizing object in the drive category. That's a really strong statement. We are not doing that. We are just saying the deformation obstruction theory of this moduli space, the one that works and gives you a way of computing invariant, is given by self-extension of R-Dot in the drive category of the moduli space. Okay, so now it makes sense that if we have, seriality in here, then the virtual dimension of this thing x1 I dot y dot minus x2 becomes 0. And why do we have seriality? Because if your curves are supported on the fibers, given that the canonical bundle is coming from the base, x I dot times the canonical of x becomes isomorphic to I dot. Or in the level of sheaves, any sheaf times canonical. If the sheaf is supported on the fiber, the canonical comes from the base, they have 0 intersections. So, regardless of x being Calabi-Yau, you have a perfect virtual dimension 0 moduli space. And so, whatever cycle that you construct for this moduli space that gives you the invariant, this is a 0-dimensional cycle in the Cha homology. Okay, so now these generating series of these invariants that you're interested in are this way. So we can fix the curve class and add over Euler characteristic. So we are fixing the curve class, and there is some parameter q that keeps track of the Euler characteristic of the sheaf. And then we can also add over betas in the vertical cohomology of x, and that is just adding these generating series with the form of a variable that keeps track of the curve classes. So it's a double sum. That's the generating series. Okay?
And why the p and beta? The coefficients in the first term.
This one. These are, yes. So p and beta. So I should have said it here, thanks. So this is virtual dimension 0, so p and beta is integral of the appropriate cohomology class against the appropriate virtual class. But virtual class is 0-dimensional, so you integrate 1. you count points basically.
Mm-hmm.
X P and X beta virtual.
Mm-hmm.
That's the definition.
Okay. Is it clear that it is always finite?
Hmm?
It is always finite, right?
Yes. For every fixed. Okay. Whenever you have a non-proper moduli space to make it a finite thing and a computable thing, you use localization and things like that. If you hope that you have some torus roaming around. Okay. So that is just the definition of these things. I'm going to show you some formulae for this. Okay. Now I don't prove much in my talk, I just want to state the results. So some of these are technical, some of them are actually you look hard, but if you know the machinery, it's just manipulations, algebraic manipulations. So I just state the results. So just to tell you a little bit about the virtual cycles, there is a theorem by PT themselves, it's a 2009 theorem, that moduli space, stable pair moduli space comes with a perfect obstruction theory. So there is a perfect obstruction theory on this moduli space P. Let me define each time, I don't write it like this, so let's define P to be this. So there's a perfect obstruction theory on this moduli space. So if this is the obvious maps, this obstruction theory is defined by R pi P lower star. As I told you, it's the self-extensions of the because you're defining something for the whole moduli space, it's a universal object in the direct category that represents our universal sheaves and sections. So maybe I call them I dot tilde. Or I dot tilde times the relative canonical or dualizing sheaf. And there's this trace freeness that you need to include there to make sure that there are no automorphisms and so on. And your obstruction theory now literally has only two terms. If you don't take the trace free, you have automorphisms and you have by Serre duality, or by just duality, which looks like Serre duality, you have automorphisms and dual automorphisms. And we don't like that. Okay. So there is this object in the direct category of x times b, p, and this object has a map to the potential complex of your moduli space. You push it down over here, and you get a map to the potential complex. And this has the nice homological conditions, which tell you that this is a perfect obstruction here. Basically, in the level of H0, you have isomorphism between the two, and in the level of H minus 1, you have a surjection. If you don't have this condition, I mean, if your space is smooth, for instance, then you can use just the potential complex itself. There's no problem with using that. But the potential complex often has infinite many terms, and you don't want to do that. So this is a nice perfect approximation of the potential complex. And we call it obstruction theory, or perfect obstruction theory. Okay, so this is the thing that for the smooth projective threefold and the moduli space of the stable pairs gives you the deformation obstruction theory. And in order to now, it's defined. So this is defined by PT, beautiful work of PT. The point of my talk today is that you would like to kind of relate this to things that you can calculate. This doesn't say anything about calculations. So the structure of this threefold is special. It's a K3-fibration on a curve. And maybe one way of actually looking at this is that maybe this object which captures, movement of these sheaves supported on curves inside the ambient threefold, we would like to relate it to the movement of curves inside the fibers. And then maybe some deformations which are induced by infinitesimal deformations of the fiber. So in some sense, it's like superposition in mechanics. You have a motion, and the curve is moving inside the threefold, and that object sees it. But this curve has two parts of deformations: movement inside the fiber and movement of the fiber inside the ambient threefold. So you would like to really analyze the composition of this kind of deformation and relate the object to that object to obstruction theories of the fiber and maybe some extra piece. That's what we would like to do. Okay, so how do you do that? Maybe I show you some exact sequences, and then after that everything will become absolutely crystal clear. So the universal complex that represents this universal sheaf and dissection satisfies an exact triangle. It's like this. It's the universal exact triangle. Okay? So what is F? F is the universal sheaf. Universal sheaf. Universal sheaf. So the fiber of this guy is two-term complex. This is some complex in the x cross p. The fiber of this on every point of the moduli, this gives you a sheaf with pure one-dimensional support in x, that together with z. So there is this triangle. Exact triangle. Natural exact triangle. And what can you do? You can apply or omega pi to it and see what you get. So okay, so if you do that, you will get something like the following. So I dot f goes to I dot shifted by 1, right? And then goes to f times omega. Everything is times omega. Then goes to I dot omega. Also shifted by 1. I'm not doing anything really difficult. It's just, you know that our universal sheaf and dissection is a two-term complex, and there is a universal object in the graph category that represents it. On x cross p, this exact triangle exists, and you apply this to it. Okay? And why are we doing this? You see, the natural deformation obstruction theory of this moduli space of stable pairs is something very similar to what you have seen in the Hilbert schemes or the Kut scheme. Remind yourself of the Kut scheme. The Kut scheme, Grothendieck's Kut scheme, is something that parameterizes quotient sheaves. Yes? So this is the construction of Grothendieck. So you parameterize this scheme that gives you quotients like this, right? And then there is a kernel. If you look at those constructions, you will see that the tangent space of the Kut scheme at every point of the Kut scheme to the tangent of Kut at a point given by this quotient f, maybe a point given by this quotient f, is a homomorphism in space from kernel to quotient. Grassmannians have the same property, and many other things have the same property. Whereas the moduli space of sheaves is different than the Kut scheme. In order to get from the Kut scheme to the moduli space of sheaves, you need to pick a stable locus inside here and then take the GIT quotient by the stabilizers of these and that, right? So what is the tangent space of the moduli space of sheaves? The moduli space of sheaves, on the other hand, so if I'm looking at some tangent space of the moduli space of sheaves like that, at a particular sheaf, that's given by x1, f comma f. Right? So this point of view is related to this point of view. In here, it is the same thing. So the natural deformation obstruction theory, which is not perfect for the moduli space of stable pairs, is very similar to the Kutzkin obstruction theory. It's derived categorically given by homomorphisms from I dot to F from the kernel to the quotient in the derived category, if you like. It's here. So all cohomologies are distinct to understand the deformations, obstructions to obstructions, and so on and so forth. And this is the one which is the auxiliary object in the derived category, which is going to be playing the role of the nice deformation obstruction theory. Why? Because if we can show that in the level of H0, H0 is just deformation space. It captures the same deformations, then if the obstructions are different, it is fine. Right? So basically our hope is that this thing in the level of H0 is the same as this guy. And then this guy having a different form actually is what guarantees to you that it doesn't have higher obstructions. That one is bad, that one has higher obstructions, this doesn't. So it's very similar to here, and that's why I'm writing this exact triangle. It relates the natural obstruction theory of the moduli space of pairs to the one that Panchapandi and Thomas construct. Okay, so that's one exact triangle. Okay. Alright. There is this little technicality in here. I mean, okay, so if I apply omega to this thing, I can also apply R tensor omega to this, like that, and this probably gives me something R pi lower star, omega k, and then it should give me R F omega pi 2, right? Actually, and why am I doing this? Because I would like to look at the trace-free ones. I'm applying R O to this, and I would like to subtract off a piece of O from here, but now everything has been modified by multiplication by omega, so I multiply by omega first and then subtract. I'll take it out. So if I do this, I will get, naturally by definition, I will get just a trace-free part. Because I would like to cook up this object. That's why I'm doing this. And the next thing in here is 0, so this thing just comes here, repeats identity. Okay, so this is the exact triangle that I really care about. Not that one, because I needed to take the piece of O out to look at the trace-free ones. Okay, so this is one exact triangle. After taking the cohomology, it relates the tangent space to Thomas cooked up obstruction theory, to the natural tangent space of the moduli space of stable pairs, but I would like to relate everything to the fiber-wise moduli space. The fiber-wise moduli space. How should I do that? So, consider sheaves as above. So if I have one fiber, K3 fiber, inside this thing, let's call that S. Okay? Our sheaves are supported set theoretically on the fibers. So really these are torsion sheaves inside the ambient threefold. So our sheaves F are really push forward of some sheaves that belong to OS modules, right? With the given properties. They are one-dimensional, they are OS modules, and our sheaves are just, on the fiber restriction of our sheaf to the fiber gives you the sheaf G. Okay, but this is exactly what gives me the relation between deformation of the curve inside its own fiber and the deformations inside how they are realized in the ambient threefold. So one trick that you guys you maybe very much like is that if you push forward the sheaf G and pull it back, yeah? I know that Sasha left, but he likes this. He keeps doing it in all of his papers, so we push forward and pull back. So we get the shift G back in the derived category, and we also get some G twisted by minus S shifted by 1 or something like that. This is the piece that realizes the information of the normal bundle to the surface, right? So this is the piece that realizes, you know, deformations of the fiber inside the ambient 3-fold. So for instance, now if you just apply R hum G to this thing, it is a nice thing because R hum G gives you the deformation in the fiber. R hum this thing with G comma G by the left adjointness of the left drive pullback and the right drive pull forward gives you R hum of I lower star of G comma I lower star of G. So in the middle you will get R hum FF. So here R hum GG, R hum FF, and then there is this piece. It will this is R hum G minus S comma G. And this minus S goes on the other side, which is the normal bundle to the fiber. So this is the piece that understands deformations of this curve realized as in the 3-fold because of the deformations of the fiber. This is that extra piece. This is deformations of your sheaf, whatever curve inside the fiber, and this is the total deformation. This is the superposition. Okay? So this is for sheaves, and you can do it also for pairs, or pairs of sheaves. So this is just for sheaves. So if you do it for pairs, it will be something like this. So for pairs, I can use, I can ask what happens if I pull back one of these complexes in the ambient 3-fold, then put the subindex X in here so that we know it's in the ambient 3-fold. I will get some complex on the surface S, and then I will get whatever remains, the remaining part, without any shift. It is because this object really looks like O to F, this object looks like O of S to G. O is a locally free sheet, so you know, tensoring with the drag tensoring with the divisor actually is the same as tensoring. So you don't get the O goes away, and then it's just the G that remains. But G is a torsion. Okay. So everyone clear on this one? Any questions? So far. Okay. So now if you apply something like apply I dot G this thing, I got S this thing, and you will get the second exact triangle which I was talking about. So you will get something like let me see, let's just write it I dot S goes to R again, left drive pull back and right drive push forward. So R I dot of X, and move this over to this. So I want to do this way, like this, and then I have I dot S. Something like that. You see? Okay, so this way now you can see that, I mean, deformations of your complex in the 3-fold get related to the fiber-bus deformations. So by these two exact triangles, you can actually relate tangent space of the moduli space to the tangent space of the fiber-wise moduli space, and the obstruction as well, and together with the extra contributions coming from movement of the fiber. So basically, things which are induced by this procedure. Okay. So that's all I wanted to say. So, how much time do I have?
23 minutes.
How much?
24 minutes.
What is it?
Sorry, number 50.
Okay. Okay, so just the message is that yes, so there is this artificially cooked up obstruction theory which works. We related to the natural obstruction theory of the threefold. We related the natural obstruction theory of the threefold to the fiber-wise obstruction theory. So using these two, we can actually say the following. So let's do this. So let's. Do I need to say everything with definition? Let PFC be a connected component of this moduli space P. We call P a type 1 component. Type 1 component if rho of PFC is equal to C, where rho is the map, natural map from the moduli space to the base curve C. So remember that we have something like this. This is pi of P, pi of X, and this also gets mapped to C, and we call, basically, we can go in here and then compose over there. So this is eligible. Okay. Otherwise, we call PFC an isolated type 2 component. So if the image under this natural projection is all of the curve, we call it connected type 1 component. Otherwise, if it is isolated, we call it type 2 component. Okay. So why is it? Because sometimes these sheaves, they are just, you have a sheaf, so you fix a curve class. Let's just look at the curves. If you fix a curve in a K3 fibration, if I told you that the fibers are allowed to have infinitesimal deformations and these curves are algebraic curves, holomorphic curves, then two things can happen. One is that under these deformations, the curve could deform to a holomorphic class, which means that the component that parameterizes those cohomology classes 1-1 class is a connected component, or that the curve doesn't. The curve class is given somehow that it gets out of the nodal locus. So those induce some isolated components of the moduli space of stable pairs. After all, the stable pairs are some decorated sheaf theoretic objects which have numerical data parameterized by these curve classes. So that's why in the level of the moduli space of pairs also we have two types of components. The components where the curve class is somehow that doesn't care about infinitesimal deformations on the surface, and the components which are isolated. So we call them type 1 and type 2. Okay. Okay. So if you have something like this, let P of 1 be the union over all type 1 components of P and P of 2, the union over all type 2 components. Okay. Now some notation. So we can write X times P goes to C times C. This is pi and this is rho. And you have the diagonal embedding of the curve inside here. And you can look at the fiber product of X times the moduli space over the curve, right? So this I would call the universal divisor. What I just told you over there, this is that S. So point-wise, you have the fiber. You can embed a fiber inside the ambient threefold and play this game and relate sheaves in the threefold to sheaves in the fiber and so on and so forth. But in the level of the moduli space, you have a universal divisor that you can play the same game. Okay? Okay, so if you have that, by these two constructions, these two exact triangles, we can say the following. So we have, so there is a theorem there exists low relative perfect abstraction theory over type 1 components, E1, which is given by this. So let's call it something like G dot R bomb I prime. So let's call this thing map I, and let's call this map I prime P. R bomb pi prime G universal shift G I dot on this S tilde restricted to P1, and this gets mapped to the fiber-wise moduli space. Okay, this gets mapped to L dot of P on C. This is the fiber-wise moduli space. Fiber-wise moduli space on every point of the curve. Let's look at the threefold, for instance. If you have stable pairs, I can ask you what do they look like on the fibers. On the fibers, they are given by complexes on the divisor S, on the fiber, which parameterize OS to G. I called it G. This is the family version of it. There's a row relative fiber-wise deformation obstruction theory for these components, for connected components. Moreover, maybe A, B, there also exists a perfect obstruction theory over isolated components. Isolated components. The isolated components of the moduli space are honest moduli space of pairs on the fiber. The difference between connected type 1 components and isolated components is that type 1 components have sheaths which deform in the fiber together with the deformation of the surface in the ambient threefold. Isolated components, they do not have that deformation outside of the fiber. So there is a perfect obstruction theory for isolated components, and this I will put in here. Let's call it G dot of 2, G dot of type 1. This is, again, same thing. R I prime P, some universal shift G. But this time you restricted to P type 2 component, you shifted by 2. There are these two obstruction theories. Fiber-wise, for type 1 and type 2 components, there is a fiber-wise obstruction theory, and for type 2 components, we don't even need to mention fiber-wise. It's a fiber moduli space. Okay? So now the exact triangle I put in the beginning, where you can relate threefold to twofold and plus extra contributions, you can actually relate it to this thing and write down the following formula. So this is our theorem. So maybe a proposition. So maybe I just tell you the following. So we can do the following: the restriction of virtual class of the obstruction theory E dot, which was the one R pi P I dot, that's the dot I, this one. and delta T to the type 1 and type 2 components can be written in terms of G dot 1 and G dot 2. You know that there is a way to relate the threefold theory to twofold theory. So in particular, after restriction and playing the game I played there, you can relate this to these two. For type 2 components where the moduli space is isolated, literally this thing, you can expect that this thing becomes exactly this thing. It's an isolated component. And for type 1 components, you can see deformations of the sheet in the threefold, plus fiber-wise deformations, which are given by this guy, plus extra contributions. So that in the level of virtual cycles is written from the way. In particular, this induces the following identity for the virtual cycle. Is for the virtual cycles. Okay, so this is good. So if I look at one of the type 1 components, and I construct a virtual cycle of that with respect to the Thomas virtual deformation obstruction theory, it will become fundamental cycle of that component. These are the smoothest spaces, by the way, so I will make a comment. So by work of PT in 09, PI and P2 are the smooth moduli spaces. So fiber-wise, these are smooth. The total space of these fiber-wise moduli spaces is also smooth. So what is it that we are doing after all? It seems that we are not doing anything. We are doing a lot of things. This is a smooth moduli space. We are putting a nice obstruction theory. So this is a smooth but obstructed moduli space, and we just relate the obstruction theories in the threefold and the fiber-wise moduli spaces to each other, so that we can calculate things. We would like to just we are aiming at calculating everything on the surfaces. That's our aim. Plus, so this is some relation. So C1 of O star of K, Artan class of the cotangent bundle of the relative fiber-wise moduli. So by work of this P1, P2, and the fiber-wise moduli, all of them are smooth. So this is one relation. Second relation is for type 2 isolated components. This thing is, again, fundamental cycle, C top of cotangent bundle of this type 2 component. And this is rho, this is the map rho. This is mapped from moduli space to C. And this line bundle is something, this is a line bundle where pi lower star of x of omega pi is. If you push forward onto x, the relative canonical, the relative dualizing sheet, you will get the line bundle on x, and then you can pull it back by this map rho to the y. So some contribution. This is some calculation. Okay? Okay, so what is the point? Now I can define invariants. Integration against these classes. Now that we relate the deformation of these pairs in the threefold to the fiber-wise deformations, we can calculate. So generating series of invariants. So let me diverge a little bit to something that many people today talked about. So let, I call it new R2 pi over star of Z onto this curve C, be the local rank 2, be the rank 22 local system. Local system given by the vibration, given by the middle cohomology of the K3-fibrations. So given by the middle cohomology of K3-fibrations. So H, the middle cohomology of the K3 is the integral cohomology of the K3 gives you a rank 22 lattice. And for the whole vibration, you get the rank 22 local system. Yes? So, of course, to this local system, you can construct a moduli space of Hodge structures for the vibration. Right? So if you give me the local, rank 22 lattice for one K3, I can look at the moduli space of Hodge structures for that K3. Now for the whole vibration, which I called it pi or something, I can construct a pi relative modulus with pi structure. Right? So that M of nu, for instance, denote the pi relative moduli space. Moduli space of Hodge structures. Hodge structures for this K3 vibration. Then there is a map. There is just a map from this end nu to C, obviously, such that it's fiber over some point, such that like this, such that for some point in the curve, M nu C is the moduli space of pi structures on S given by pi inverse of C. Not only you have a map that way, you also have a section map from here to here. So they also from that, and so there also exists a section, let's call it sigma from this to here, which takes, so if I pick some point in the curve, sigma C is the Hodge structure determined by the.
Yes. How does exactly M nu related to the period map?
How is it related to the period map?
Yeah. So, what is it? What is Hodge space structure?
You give me a rank 22 lattice, you projectileize that, you get to 22-dimensional, 21-dimensional space. Then you pick a linear, one-dimensional linear subspace given by some force.
Okay.
Right? Omega, which is isotropic basically, like omega. You know the thing, right? So that gives you a decomposition of this thing into a Hodge structure of type 121.
So what is this form?
Hmm?
What is this form?
Any form. Any form that satisfies, the usual relations. So you would like this to be 0, and you would like this to be bigger than 0.
Sorry, kind of form.
So this is for one, yes, exactly. So this is for one fiber, right? Now you can do this fiber-wise. So for one fiber, there exists a modular space of Hodge structures of type 121.
So each fiber is just a curved space.
Yes. And now you're looking at the total space of this
Okay, so
curve.
So it's not related to I don't know how is it related to the Hodge structures of the fibers of our.
It's not going to be that. So I'm just yes, this is digression. So this is so we know about this thing, and our curves are supposed to become holomorphic curves, right? Remember that I discussed about these curves. We would like them to remain holomorphic. So what I'm trying to do is the following. So inside the high relative modular space of Hodge structures, for any fixed curve class, there's a nodal Lefschetz device, which parameterizes 1-1 classes.
I see.
Right? Now what am I doing? I'm saying that from this modular space of Hodge structures, there is a map from C, and there's also a section map from here to here. Yes? So maybe actually I do it this way. So this is the pi relative modular space of Hodge structures. Fix a curve class beta in H2. There's a divisor which parameterizes all such curve classes which are H2 intersected with H1. So this is the nodal Lefschetz device. So points in here are 1-1 classes, right? Yes. Now there's also this map from the base curve into here. You pick a point, you send it to the Hodge structure determined by the fiber that lies above that point. If you look at the image of this curve inside here, it comes and intersects this nodal Lefschetz divisor inside here. So it intersects. So maybe it falls sometimes in the light. So maybe I like that. Okay? Then you can do intersection theory of the image of, you can intersect the image of this curve and this nodal Lefschetz divisor inside the modular space. You can. Or you can take this divisor, call it D, pull it back to the curve integrated on the curve. This is the same thing, right? By push-pull formula. You will obtain a number. That number is a nodal Lefschetz number. What does it parameterize? It parameterizes the number of fibers in a K3 fibration
where
your curve is holomorphic.
Okay, I see.
And that number must show up in the stable pair invariant for the K3 fibration. Because our curves, the curve part of our stable pair needs to always remain 1-1. We want that to remain an algebraic curve. Our sheaves are supported on common algebraic curves, 1-1 curves. Okay? So now that I said this, so in these components where you have some connected components, you do excess intersections. You look at the normal bundle to the divisor and intersect it with the curve, something like that. So this gives you a nodal Lefschetz number. Okay, how is it related to this picture though? Okay, it's related the following way. It has to do with these connected components which I mentioned. So if you have something like that, now so I'm just repeating what I drew in here for C for some point in the curve and an irreducible curve class beta in these vertical classes and some number, integer number z, we define some locus, we define mu c to be the mu c of h and beta, to be the set of gamma and mu c such that self-intersection is 2h minus 2 and push forward that this gamma is equal to beta. And this is the push forward inside the ambient threefold. Remember that we are picking curve classes in the threefold, but we are looking at them inside the surfaces. So you might get 0 curve classes when you push forward the curve classes into the ambient threefold. Okay, so you get this locus, and then let EC for point C, EC of H beta inside this locus be the subset where gamma is a 1-1 class in cohomology theory of the fiber. So there is this thing on S equals to pi inverse of this point C. It depends on the point on the curve, self-intersection of the curve and the curve class. There is this. So then you can now define EH gamma to be the union over all points of the curve of these things. Something like that. And we can see that B can be written, BH gamma can be written as this joint union of two components, the isolated and the connected ones. So B of H gamma is written as a type 1 component and an isolated type 2 component. Okay? So, this induces map, let's call it epsilon, B1H gamma, to the base curve C. This is that type 1 component, which covers the curve, and of course there is a component in the moduli space of stable curves that is induced exactly by this connected component. So now let P of epsilon be the connected type 1 component corresponding to this map epsilon. I know exactly what the virtual cycle looks like. I know exactly over the different type connected components of the moduli space what it looks like. All I need to do, I need to restrict the virtual cycle to this particular connected component and integrate over it. So that's what we do. So and let P of n epsilon be defined as integral against this connected component with the virtual cycle induced by the original obstruction theory, integral of 1. Now we have shown by our result, we see that this virtual cycle for a connected type 1 component satisfies a relation. It is equal to, everything is smooth again, P of epsilon, intersected with some first term class of the pullback of the line bundle that gives you the canonical of the K3-fibration times top term class of the fiber-wise cotangent sheaf. This is exactly a repetition of the previous formula, but this time we know exactly which type 1 component this is. This is the one induced by our curve classes, the holomorphic curve classes. So, and I will be done in a few minutes. So all you need to do is just integrate against this. So, and for isolated components, also we have a similar thing. We know exactly what the virtual cycle looks like over any isolated component, in particular this component induced by this. So let's call it P of B2 maybe, like that. P dot virtual is P of B2, C1 of that, dot term class of P of B2. That's it. That's a isolated component, so that's it. Okay, so we have these two relations, and now we can integrate against the cycle. So now I can integrate against this virtual cycle. So for instance, for type 1 component integral, you're integrating 1 against this, which is the integral of 1 against this guy. So what would it be? This goes to the base. So this will be just integral over some smooth locus. They were like this, but C top omega times C1 of the rho star of K. This whole thing, this is the total space of some fiber-wise and smooth moduli space. So you can integrate over the fiber and then compute the contribution of this to your integral separately. So this becomes minus 1 to the n minus 1. Euler characteristic of the fiber-wise moduli space of the K3, decorated with these numerical data. This is the self-intersection of our curves, and this is the Euler characteristic of our sheaf. Times integral of C1 of this line module. Sorry, epsilon. Everything, the maps are not epsilon. Like that. And Pandey and Thomas showed that, in fact, this is over the P epsilon. They showed that this is exactly, remember I drew a picture. This is the nodal Lefschetz divisor. The curve comes and intersects this thing, but sometimes it falls inside here. These are those type 1 components. Then if it is like that, you integrate, you calculate the normal bundle, and you use excess intersection theory to intersect this with the curve. Turns out that this exactly captures these. This is the normal bundle. When you pull it back to that component, exactly is the normal bundle. So this integral becomes the nodal Lefschetz number for the fibration with the data that you needed. So how should I call it? Okay. And for the type 2 components, there is not much to worry. You just integrate over the isolated fiber-wise modulus. Similarly, here n of B2 becomes integral against B2 of C top of omega P. So this is just and K3-H. Yes. Okay, so fiber-wise invariants are just Euler characteristic of the fiber-wise moduli spaces. Those ones that have connected components, where the curve class can have deformations into one locus, they are given by fiber-wise Euler characteristic of the moduli space times the nodal Lefschetz source. Now you can put all of these into a generating series. So it's like we are putting them all. Sometimes the coefficient is just 1. Coefficient of this guy is 1. Sometimes it's nodal Lefschetz, certain nodal Lefschetz number. We can put them all in a generating series, and this is what we have proved. This is 2016. With the collaborators, we proved that P0 of x eta, where you fix the curve class, becomes some sum like this, some double sum like this. Euler characteristic of Pn K3H times nodal Lefschetz numbers of this. Okay? why is it that, okay, so this is the last thing I wanted to put in here. This is just for the smooth vibrations. Why is this that this sum is interesting? I won't put it here because it takes one blackboard to write down. These guys, these numbers, these can be read off from a modular form. So there is this modular form, very famous for enumerative geometers, Kawai-Yoshioka. So these numbers can be read off from Kawai-Yoshioka modular form. And this also has a generating series, which also is a modular form. Borchardt, actually. Borchardt main work on nodal depth theory. Borchardt's. So you can see that when you're looking at the K3 surface, if you're counting curves or points on the K3 surface, you get a modular form. If you embed the K3 in the K3 fibration, if you restrict your curve to lie on the fibers, again it's a modular form. It's not that trivial because we are not just honestly, scheme theoretically putting the curves on the fibers. We allow them to be set theoretically on the fibers, but they can have deformations outside. This is kind of non-trivial. So we'll get these modular forms. I didn't discuss about nodal fibrations. You can do this all for nodal fibrations. If your fibration has finitely many rational Galois singularities, there is a mechanism to smooth out the fibration. You get this result for the smooth fibration, and then you relate it to nodal fibration invariance. It's all in the paper. There's also some conjectures we made, I don't have time, about relation between these and the non-commutative version of these things. So it's also in the papers, like pair versus stable pairs, we define them, we relate them to each other, and so on and so on. Okay, I stop here. Thanks for your attention.
Any questions?
Yes, Rossi. Which I learned. You shouldn't say Rossi, yes. You should say yes, Rossi. Do you have any questions? Yes.